Hello everyone. I am excited to present our work, From Cognitive Priors to Instance Semantics, a unified framework for multitask affective computing. This work aims to unify three core affective tasks into a single, unified framework. Human affect is typically modeled through three perspectives. First, expressions recognition, like happiness or anger. Second, action units, which describe local muscle movements. And third, velocarousal, which represents continuous emotional dimensions. Typically, these tasks are studied separately using different datasets, such as RAFDB for expressions or DISFA for AUs. However, unifying these tasks faces three critical challenges. Challenge 1 is disjoint annotations. Real-world datasets rarely provide all labels for a single image. Most data is partially labeled. Challenge 2 is negative transfer. When training jointly, tasks often conflict, dragging the optimization in different directions. Challenge 3 is task performance misalignment. Different tasks converge at different speeds, making it hard to achieve optimal performance for all tasks simultaneously. To address these, we propose COIN, a two-stage framework. It bridges cognitive priors with instance semantics derived from vision language models. The framework consists of Stage 1, Cognitive Cog-Expert Co-mining focused on cognitive knowledge transfer, and Stage 2, Expert and Semantic Knowledge Integration focused on cognitive and semantic knowledge integration. Let's look at Stage 1, Cognitive Cog-Expert Co-mining. Since labels are disjoint, we use cognitive knowledge to generate pseudo-labels. We know that specific expressions, like happiness, are inherently linked to specific AUs, like cheek razor. We designed two pathways, expression to AU path, infer AU targets from expression predictions. AU to expression path, infer expression targets from AU labels/predictions. By enforcing these cognitive consistencies, we can propagate supervision across datasets and train three task-specific expert models, which we call cog-experts. In Stage 2, we introduce the expert and semantic knowledge integration architecture to solve task conflicts. It has a dual-branch design. The task-specific branch distills soft labels from the Stage 1 cog-experts. This stabilizes training using teacher knowledge. The semantic alignment branch is our key innovation. We utilize the VLM text embedding to align our visual representations. We introduce static and dynamic prompts. For static prompts we introduce class-conditioned prompts for global context, and for dynamic prompts we propose instance-adaptive prompts to capture fine-grained details. This aligns visual features with rich semantic descriptions, greatly enhancing generalization. Our experiments show significant improvements across the board. In Table 1, COIN achieves state-of-the-art performance on expression, AU, and VA tasks, outperforming strong baselines like Clipper. In Table 2, we compared COIN with large vision language models like GPT-4o. Crucially, in Table 3, we compared our Stage 1 strategy against standard multitask learning methods like MGDAUB and GradNorm. Our proposed E2A and A2E losses consistently outperform these complex gradient balancing techniques. This proves that solving the disjoint annotation problem via cognitive mining is more effective than just balancing gradients. COIN significantly outperforms these generalist models on fine-grained affective tasks. We also evaluated robustness and efficiency. Table 4 shows our generalizability. Even on the unseen FWild2 dataset, COIN generalizes well without direct training. Table 5 demonstrates that despite the dual-branch design, our method remains computationally efficient with low inference latency, making it practical for real-world deployment. In summary, COIN is a framework to jointly solve all three affective tasks using disjoint data. By combining cognitive mining and semantic alignment, we effectively mitigate disjoint annotations, negative transfer task performance misalignment challenges, and achieve robust performance. Thank you for listening.